Good evening, everyone. I think it's time to officially start today's event. We expect a few more attendees, but we'll let them in while the talks are in progress. So this webinar on ocean bottom nodes is the first in a series of events planned for this year and dedicated to acquisition. Nodes are known to be one of the best options currently available for offshore seismic imaging. Due to the wide azimuth nature of the data that they record, they are very convenient for velocity model building in complex areas. Multi-component sensors embedded inside nodes record converted wave via 3C accelerometers. This gives access to shear waves velocity information and provide the raw data needed to produce an alternate image of the subsurface free of fluid effects. For the processing of PPPS data acquired with OBN also offers a way to better discriminate between the pressure and fluid saturation change within the reservoir in the case of 4D monitoring. So we could also mention the specific processing step that are possible with OBN data. For example, PZ summation and up-down deconvolution. We could list many other additional advantages of nodes over conventional marine streamer data. However, nodes are much more costly than standard marine surveys, and they must operate in very challenging conditions, staying on the seafloors for weeks or sometimes for months without any external power supply. So improving the nodes sensors, the acquisition design or the operation turnaround with new technologies is really a field of very active research at the moment. And the speakers invited today will give you a quick update on some of its latest advances. Reducing OBN acquisition costs without compromising data quality is especially critical for the future of this technology. Reducing costs would open seismic exploration to larger areas if we think of conventional oil and gas targets, but it could also ease the development of new applications such as carbon dioxide or hydrogen storage site selection and monitoring. We could also imagine a much wider use of nodes by academic research with reduced cost. Before we go into the heart of this topic, let me say a few words about EAGE and the chapter itself. The association was created in 1951 and is focusing on the promotion of innovations and applications in geoscience and related engineering subjects. It's a professional not-for-profit association for geoscientists and engineers. And this association is run by a group of volunteers from the beginning. The association aims as well at facilitating communication and cooperation between the different stakeholders of geoscience. We have members basically on every continent, even though a large majority of them is in Europe, of course. To achieve its goal, EAGE is developing activities in various fields. We all know the conferences organized on a yearly basis, but EAGE is also taking care of various types of publications, conference proceedings for sure, but also technical papers in professional journals. As regard education programs, a lot of short course and training are regularly proposed.
Hey.
Speaking of conferences, don't miss the next annual conference that will be held in Oslo this year. You could also join the fourth EAGE conference on digitalization that will take place in Paris around the end of March this year. Why should you join EAGE? Becoming a member comes with several benefits. among many listed here on this slide. We could lay the emphasis on a few. For example, the access to EarthDoc, containing a wide range of conference abstract and technical documents. The yearly subscription to First Break and another more specialized journal. This counts for all EAGE events, conference, courses, and access to learning resources. Basically, this membership gives you access to all the tools you need to keep up and improve your geoscience skills. The EAGE is also encouraging the development of local technical communities. The local chapter Paris is one of them. Local chapter London is also joining the call today. You can see Artem on screen. And you will get a chance to get acquainted with them, as they will present a few slides as well. In terms of chapter staff, all board positions are filled, but we keep on searching volunteers to widen the range of expertise of our team. This is important in the long run, as it will allow us to prepare events dealing with a large variety of subjects. Okay, let's move on to the events program. Of course, the events program for this year is still under construction, but let's take a quick glance through milestones for this first half of the year. After the data management event from January and today's webinar, we'll continue with 2 other talks dedicated to acquisition. The next one in March will deal with ongoing data acquisition campaign in Svalbard, small island of Norway, and it will be delivered by William Arcourt from University of Aberdeen. And the 4th of April, a technical session dedicated to geomechanics for industrial storage of carbon dioxide and hydrogen will also be proposed, and we'll talk about it in more detail at the end of the webinar. Well, we have a LinkedIn page, of course. Please follow it to keep up to date with the latest events organized by the chapter. And don't hesitate to email us as well if you have webinar topics to suggest, or if you wish to volunteer for a presentation. As mentioned earlier, EAGE Local Chapter London is a special guest for today's webinar. So Artem, are you ready? If so, we'll let you share your slides and introduce yourself and your team.
Thank you, Guillaume. Let me share my slides, and I will steal another 3-5 minutes of your attention by advertising the activities which we had and which we are planning to have in London. Let me try sharing my slides now. Take a few moments. Okay, I should be sharing now. Guillaume, can you see my first slide?
Yes, we do see your first slide.
Okay, great. Thanks a lot. So our main presence is on LinkedIn. So this is our title page. And if you are interested to join us and to follow, so here is QR code. Please scan it. Or if you cannot scan it fast enough now, then just go there and type for EAGE Local Chapter London. So there you can join us and you can follow and see the posts and activities we are planning. So who we are? So we are really the representative of different companies and universities from the London area. So we have President Selina, who is driving the team. We have Vice President Azza Salem, myself as a secretary and a part-time treasurer. And secretary, we are looking for a replacement volunteer to support this role. So if you are in a local area in London, or even maybe not that far, some of the activities can be done online, so you don't necessarily have to be local in London for that role. Head of events, we have Liesl Lewis and Joseph Sutcliffe, and also because more merrier, we are always looking for volunteers and people who can make things done and who can arrange things on technical side of the things and on the fun side of the things. So Joseph is also doing communication duties for our chapter. So we were established more than 6 years ago. Our first event was on 27th of April 2017. We had a nice talk by Ian Jones. Our technical meetings in the past, they were in person, normally hosted at Imperial College London. And after the talk, we usually go for socializing in the pub or somewhere else. During the difficult pandemic years and post-pandemic years, we reduced the number of in-person events and went online. So here is a little bit of summary of the previous 2 years from 21 to 23. So we managed to have only a couple of in-person events, but instead we made like 10 online events which were broadcasted globally, worldwide. So, and that actually triggered very interesting phenomena that not only local participants, but global audience were able to attend our meetings, and we made a global outreach for that, which we can see from the Eventbrite statistics. So every event which we are planning, we are announcing it on Eventbrite like a month or couple of months advance. And the Eventbrite nicely picks up the location of the people who register there for these events. So for this period of time, for these 2 years between the 1st of April 21 and last of March 23, we had 1,223 people registered. So it's not necessarily all of them attended these events. So we can say that maybe half of them or even less attended for all these total events, but the global footprint is quite impressive. And that triggered our thinking and a shift in paradigm. So we started to arrange things in offline as well as online, and sometimes even hybrid. But of course, all these arrangements, they take a bit more of efforts. And but additional advantage if we arrange it online. So in those occasions when the speakers are all right with that, we are recording the talks and we are publishing them in YouTube. So you can go to EAGE official channel and you can search for the video recordings from our chapter as well as other chapters, like for instance this talk by local chapter Paris. I don't know if it is recorded or not, probably will be clarified at some point, but many talks by the local chapter of Netherlands and Germany and so on, they were published in YouTube. But the nice thing to be local is not only to go and watch YouTube, but to walk outside and to look at the actual rocks. So that's an example of our field trip, very local field trip in London, where we had a guided walking tour around London with Bob Leppard. He told us about buildings and stones used for this building in the central London. This was quite interesting. And part of that, we have some other local excursions, field trips, and fun activities. So for the plans, exactly in a week's time from now, next Thursday, we are planning a joint online event with the local chapter Houston. So we have Christoph Stork. He will talk about realistic modeling of difficult lens size noise and some tests of removing it. So please join. It's online, so anyone can join. Then in March, we are planning a hybrid event. So now we are in negotiation and trying to arrange our local standard location at Imperial College. It will be in person with some follow-up of socializing reception event, but also we are planning to broadcast this event. So it is not published on Eventbrite yet. so actually one slide back. So Chris Stork event is already published. So if you're interested, I encourage you to go to Eventbrite and register for that event in 1 week. So this event in March is not published yet, but we have a preliminary agreement with Tom Reimer from Down Under Geophysics, and he will tell us about the fancy new FWI imaging techniques and future of processing and imaging. I'll put a note 21st of March for that. April, here's a bit of experimental setup. We will have Claudia Strobia, and it will be a joint event between EAGE local chapter Pau, Paris and London. So Claudia is based in Pau, and for this event on 18th of April in the evening, we have an ambition to have it hybrid, so offline in Pau, and will be broadcasted online worldwide. So put a note and join it. And but because it's late in the evening, so we also Claudia agreed to make the same talk on the next day in the lunchtime. So the previous talk will be on 18th of April. This is Thursday in the evening, and the same talk will be repeated online only on Friday lunchtime. So if you're interested in that, book yourself on either of the events. And if you want to present something, if you're based locally and even not locally, but want to raise your global visibility, please contact us via LinkedIn or using this email, eaglondon@gmail.com, and drop us a line if you want to participate as a volunteer or if you want to give a technical talk for us. And as a highlight, so we were elected as the best local chapter of 22 a couple of years ago. So that's all from me. Thank you, Guillaume, and I'm returning the stage to you.
Thanks a lot for this nice chapter introduction, Artem. And the attendees from UK, don't hesitate to volunteer and join the team of Artem.
Yes, please.
Okay, let's now move on to the agenda for today. We have 3 talks planned. Presentation should last up to 7 p.m. and we'll conclude the webinar with a Q&A session. Feel free to post the question in the chat during the presentation. We will collect them, and at the end we'll read them out at the onset of the Q&A session. It's my pleasure to introduce our first speaker, Ted Manning. Ted will give us an overview of BP's vision for the future of OBN and seismic in general. He is working as a senior principal for innovation and technology at BP. In addition to this role, he also belongs to Marine Autonomy Working Group and contributes within Ocean Seismic Service and Sprint Robotics committees. He has a wide range of expertise in geophysics, from seismic acquisition to processing, modeling and research. He also built up skills in technology development and leadership, digital transformation as well. I got the opportunity to work on various innovative acquisition types, multi-azimuth acquisition, ESS blending, HD sampling, or development of the nimble nodes. With an educational background in geology, geophysics, and computer science, he started his career with Western Geco in seismic processing roles before joining BP. Ted, if you are ready, the floor is yours.
Great, thanks. Thank you, everybody. I'm just hitting the present button in Teams. Is that working?
Try to share your slides again, maybe.
It's opening PowerPoint Live, so I think it'll take a couple of seconds. While that's opening, I'd just like to say thank you for. Yes, it's all good. Thanks for the opportunity to EAGE and the kind invitation to speak today. Thanks to everyone for making, giving of your time to attend as well. Hopefully you'll find it interesting. So my topic today is around sustainable seismic and the key technologies. And these are complementary technologies. They work independently or work together even better. So with that, I'll get to my content slide. So I'm going to start with one slide, 30 years in 30 seconds of seismic technology evolution. I'm going to start with another, I'm going to continue with another slide on sustainable seismic. What's the motivation for that? And then I'm going to spend most of the time giving you a very quick recap of each of the different technologies that are in play here. But I wanted to bring up the topic as well that the design of experiment to get our seismic images is reliant not just on the technologies and equipment and the processing, but obviously the constraints of those equipment. There's a lot of like cost, you already mentioned, that's a constraint. But the amount of equipment, the inventory, the time that we have, these are all constraints, and technology also has to address these. And I'll wrap up with one slide. So 30 years. So I've fortunately joined industry in '95, and I've had the pleasure to be involved in these technologies. But BP has had a privileged position, I think, to be, front and center innovating in a lot of different challenges that meet the imaging challenges that we've had to deal with as a business. So life of field seismic, wide azimuth streamer, multi-azimuth, full waveform inversion, deep water nodes, the blending of blended data, right, where we separate source arrays and receiver arrays into point sources and point receivers and get much more sampling efficiency, and which leads directly to imaging quality. And I'll touch on this again. I'm taking it offshore, blending into marine environment again to speed up the marine cases, and the introduction of nodes and wireless equipment from cables. So the next generation of that has been equipment. We have to, unfortunately, get involved in changing some of the equipment because, again, our insights into what drives our imaging and what drives the efficiency sometimes isn't available in the marketplace. So we have tinkered with this. The Stride company, I'm pleased to say, provides the smallest, nimblest node that you can actually use to be extremely efficient and get our high channel count moved over the ground with very little impact. So an environmental impact is something we'll be coming back to time and again in this talk. But the current generation of technologies we're labeling as sustainable seismic, and that's what I'll be talking to you today about, right? So the motivation for sustainable seismic is the trade-off that we have in the world. The World Energy Council, top right here, talks about the trade-off between energy security, environmental sustainability, and energy equity. So you can have one, but at the cost of the others. And how do we balance this across the world? And technology is one of the key balancing aspects. But sustainability is a criteria that we have to look at. And at BP, we're transitioning to low carbon energies. So we're producing resilient hydrocarbons to get to net zero, but 50% of our investment as a company, our capex investment every year, goes into low carbon energies and renewables, for another word. And we have a framework by which all our operations, including seismic, has to comply. And it's very simple. So sustainability, there's like lots and lots of aims you can look at, but the three key principles to get to take away are getting to net zero, caring for our planet, and improving people's lives. And those three simple points will come up through our technology choices and changes that we're trying to make. So hopefully that gives you a bit of context for what we mean about the role of sustainability. So the sustainable seismic vision then is, I like to think of it as a picture, and I basically then think of the four different elements as different jigsaw pieces that fit together or can work by themselves. Okay, that's what we mean by complementary. In blue, we need affordable, fast turnaround, high quality data. It was an ever increasing challenge to get more resolution, more attribute quality data so that we can distinguish fluids and lithologies and so on, and pressure. We have then in yellow, we have the receiver side. So we need automated high inventory on a seabed, and we need high inventory, nimble on land. Less automated because it's a much easier environment to work in, but there is scope for automation. It's just not the first priority. In green then, we have the source side, and again, smaller sources, again, less emissions, but also more portable, less footprint on that side. And then finally in red, we bring in marine autonomy, again, moving people on shore, not full autonomy. So we don't need full autonomy. That can come over time, but we can take advantage, huge advantage, in fact, from just remote operations to start with. And these vessels are cheaper to build. They have more payload for the vessel size, and they basically have less emissions. So we get, you can obviously see the economic advantage of that. So let's start with piece one. So we're in the blue box. So wavefield sampling and illumination. That's what we're doing. That's what we're trying to acquire, is seismic energy that's returned from our source, and then we invert that or image that in some way into subsurface properties. If you plot historically all of the different surveys over the last 4 decades and more, you can find a distribution around a log linear trend. So the log linear trend in green there is a pretty good fit for the surveys that we see in our industry, land and marine, right? So all this is telling you is that approximately every 10 years, we have 10 times more data acquired for the same, footprint on the surface. So millions of traces per square kilometer, for example, as a measurement. Now, some surveys will be above this trend, some surveys will be below this trend at any given point. So the idea of sparsity and density changes over time. That's what I want you to take away from this. I put, just for fun, anyone who's interested, you can take the blue equation there and you can plug in a year, and it will tell you for any given year how many traces per square kilometer that green trend is, and you can compare one survey design against another. But again, for fun, this year we should be at 650 million traces per square kilometer, right? And that's assuming a 20-kilometer area of interest, right? A radius of, to give you 20 square kilometers. And the final point is we're trying to get sampling, not just spatially. So it's not just the distribution of sources and receivers spatially. It's also the temporal sampling. It's the sampling with offsets. The diving waves come back at very, very long offsets, for example. Azimuth, the illumination, we need to look through the anomalies in subsurface in different directions to get the best picture. Bandwidth is another thing that we sample. High frequencies, of course, attenuate very quickly, but getting on the low end is another issue. And ocean bottom nodes give us most of these by default, right? But they're expensive. So here's an example from our Claire OBN. This is a published paper, the reference there on top, Smith 2019 in EAGE, and we can see the evolution of seismic quality going from the left in 2006, what we refer to as sparse ocean bottom cable. 2010, more referred to at that time high density, and then ultra high density in 2017. As you can see, you start running out of superlatives unless we have some sort of idea of what real density is, and that's where trace density comes in as a proxy. But each of these, even then, even though these are very dense and probably one of the densest ocean bottom node surveys that have been acquired in the world, they're still somewhat behind that trend that I showed. And this is because it's not because we don't want more data and we don't benefit from it in our algorithms. It's because it's too expensive. So what can we do about that? This is a land example just to drive the point home. Again, 2 references here, a data set that I set up in 2011 in Risha, and one of my colleagues, Amin, processed, and I think many people are familiar with. The data is identical on both sides. It's acquired the same, point receivers, point sources, blended, processed. All the statics and velocities are the same based on that very high density, 41 million traces per square kilometer. And then you just decimate it back to less sampled data to see what all the benefit of processing is kept, and you can see the huge degradation of imaging, right? So this is just, again, to prove we know what the answers are, how to get better data, we just can't afford it. So the next piece of the puzzle then is, well, what can we do on the receiver side? We need to distribute our equipment very efficiently, and we'll come back to this with a toy example later. But the pace by which we can move the equipment around, deploying it and retrieving it, is a massive component of the technology so that we get the sampling that we need. I'm going to give you a land example. So apologies for those who thought you were only going to see marine, but in the sustainable world, it's land and marine. So we obviously want to collect data that doesn't impact the surface, right? So we don't want to bulldoze lines, or we don't want to cut and clear trees and so on if we can help it, and it's dangerous, and the big bulky equipment requires that we do. Here's an example of equipment we're working with, the Stride node I mentioned to you. So we have the receiver side, and we're working with Explorer's pinpoint source. And here's an example last year of an area in the US, a land example where we can deploy these tiny sources and receivers. So you can have a seismic acquisition system in your hands, one hand for a source and one hand for a receiver. And you deploy that on land, and you can then get this image, which is a mile of deep of imaging and 6 miles across. It was done in the US, so we're using miles. But we have, what is a very nice quality seismic image and no footprint. And the other point here is we were not allowed by the environmental regulator to bring any type of any type of land vibrator into the ground here or dynamite. So this was the only way to acquire it, but of course, zero footprint. So this is a really good example of sustainable seismic on land. In marine, the industry has observed what I've been talking about, the cost of ocean bottom nodes and the way that links to the equipment that we use. So there's loads of novel innovation in this space. We were quite excited to wait for the swarms of flying, swimming nodes from Spice Rack, right? But unfortunately, that technology has diverted into swimming out from a basket that's lower to the seafloor, which again is much more efficient, but not sufficient for the ambition that we have. So we started a venture with Blue Ocean Monitoring in Woodside. And we have a company called Blue Ocean Seismic Services set up from 2019, and they have prototypes collecting data. I'm very happy to say Fabio will take you through more of this later on. And then I believe we'll hear from PXGeo on their manta ray as well. So a really exciting space. So why swarms? What are we trying to do by turning every one of our ocean bottom sensors into a more intelligent, I would say a smart enough device so that it carries the payload to the seabed. So the self-navigate, land, and reposition, that's the capability that we're expecting to take us to the next level of efficiency. In fact, it's not impossible that we could start seeing this type of system replacing the need for streamers, because they will be just as efficient. So watch this space and let's see how that prediction materializes. So it's also clean tech, right? So in the sense that we can apply it for other types of imaging. We can apply it for shallow imaging of wind farm foundations or monitoring offshore CCS. So I just wanted that point to be made. And we can also consider changing out the payload from a geophysical one to monitoring other things on the seabed, such as carbon bubbles, right? So if you really want to find, is there a leak over hundreds of square kilometers of seabed, you can't monitor one or two sites. You need a lot of sampling and measurements. So here's a node on a rope example of an ocean bottom node survey we acquired last year. The receiver area and the node sampling, so it's dense, right? So dense sampling, dense on the receiver, dense on the node. And that requires two vessels, these node handling vessels on the left in blue, one continuously deploying and one continuously retrieving. We need that distance between the two vessels to be about 2 kilometers for our imaging. And that's, again, we could do with more, but it's just, you can't afford it. So that's about 5,000 nodes being actively recording. And then we do a little bit bigger on the source side because, again, we've got plenty of time and it increases the imaging a little bit. If you look at the node handler itself, then it's working at, in this survey, at about 0.8 knots, and that's 42 days to acquire this particular geometry. Picking up would be 15 days, and the source is going faster again, so you only require 25 days because it's a bigger patch. So again, you're only as good as the slowest element of your operation. So the problem is it's worse than that, because the node handling vessel is not just 24/7 deploying nodes. It's actually sometimes turning, sometimes propping down anchors, doing lead-ins, grappling for the lines to pick them back up again, and turning around, right? So all of this means you've got 66% efficiency in this case, so 64 days for your survey. And then there's weather downtime, and then there's crew changes, so it's 90-odd days to actually carry out this piece of work. So if we have autonomous underwater nodes, we can remove the need for one of these receiver vessels. And this is a day rate operation, right? So we're spending a significant amount of money every day for every piece of kit. So the shorter this can be, the faster the operation can move, the dramatically lower cost your traces are. And this is what it reduces to, is the trace cost, right? So we need efficiency. Then we can get more data and we can fit more surveys in and so on in the timeframes. So removing one vessel is one part of it. The nodes will then roll themselves, so they don't need to be picked up and redeployed. They can roll. And then because now this is so much faster on the receiver side, you can actually then bring in a second source vessel. Now you pay then twice the source vessel cost, but they're for half the time. So basically, you don't have any cost change, but you do your survey 50% quicker. And as you come to deep water with ROVs laying out one by one, this is even faster. So the next element is marine autonomous systems. So again, these are the vessels. So most ships are pretty digital to this day. There's most source vessels, for instance, are controlled by the navigation software. You're not steering the vessel anyway, but you have your crew, full complement of crew on board. So the next step is to bring many of those crew, maybe not all of them, but many of them onto shore, where it's much safer, close to tertiary care, and a much nicer working environment than bouncing around off sea. And I've spent weeks doing that, so it suits some, not everyone, but it means you can work onshore, and you can do the same work, and you use modern technology to bring in some of the data that you would have been looking at in the bowels of the ship into a working center onshore. Now, we started this 4 years ago with Ocean Infinity, have a well-publicized ambition to build Armada fleet. So a very large number of vessels, and they've built 8 78-meter vessels to date. And so we've been looking at how could that fleet, once it was being built, how could we use that in what types of use cases? So these are 36-meter vessels or 78-meter vessels. What can they tow? Which equipment can you put on them? They've got dual moon pools. Can you lower them between those or whatever have you? So here's an example of a LAR system, one of the 2 that would be on board, operating at Southampton for well over a year now, and an ROV inside of that, so you can remotely deploy and operate it and retrieve it without a crew. Of course, that allows you to deploy deep water nodes, right? So you can use smaller vessels with less crew, less emissions, less safety exposure. And 2 of these tests, one with BP and one with another company, are happening this year. For many years, I just wanted you to be aware, we've been using small USVs for site survey work, right? So that's already commercial. And you have 0 people, 90+% emissions reductions. So again, real success story in small USVs. We're talking here about big USVs. So the final part are on sources. So, again, for emissions, we talked about carbon emissions from how many vessels, how big the vessels are, how efficient they are, how long you're using them. But there's also sound emissions, right? So from our source, and we have to do quite a lot of work on our permitting for that, and it's for good reason. And we're looking at the mitigations of these sources in the permits as well. So we have to change, the expectations that we have in terms of sound levels and sound exposure levels as well as peak levels. But I'm going to give you a quick 1-slide view of work we're doing this year to try and pull all of this together in a field trial. So we're going to sail one of these 78-meter autonomous vessels from Europe to the US. But this has been a few years in the planning, but we're hoping to execute this year. Everything is on track. It's a technology collaboration between BP, Ocean Infinity, Geospectrum, and there will be some processing data to come from this as well. We will at minimum require DAS VSP data, but we may very well overlap with some ocean bottom node data in parallel and get that as well. So we compare with conventional as well as this new approach. And finally, there's a lot of stuff that we have to do, of course, not just technology. There's new processing, moving marine vibrator. There's JASCO modeling for permitting for these new sources. There are engagements with the regulators for this, what was called a new and unusual technology in the US, and other work ongoing. But I think this is quite exciting. So we'll be feeding back to the EAGE on our progress on this once we get results. So my summary. BP has been investing in sustainable seismic to support the energy transition. So it works from our legacy business, but also we're hoping to enable access to ocean bottom node data to be in more basins. We've got a survey in the Mediterranean, our first survey recently, which is working very well, but it's again really expensive. So can we start doing more of these surveys in more basins? So this is really exciting. And then can we develop this technology for renewables, low carbon energy as well? And the answer is yes. Monitoring CCS, hydrogen, storage areas, wind farm foundations, nodes are applicable for all of these. The other beauty of it is they can swim in if they're these gliding nodes. They can come in by themselves. You do not need to enter safety zones around wind farms or exclusion zones around platforms. That can save a massive headache and another costly survey cost for operating close to platforms. And on land, again, the sustainability is very relevant for CCS and geothermal and other usage. So in wrap up, sustainable seismic components are uncompromised design of experiments. So don't start designing a survey with an expectation of older technology, with an expectation of rates over the ground with bulky, heavy equipment, or slow deployment and retrieval mechanisms, or even inventory limitations. We should look to solve that in technology so we get the best algorithms and imaging for the subsurface. We want then nimble equipment and low maintenance, because if we go autonomous, we'll have less people offshore. So low maintenance is certainly at least during the survey. In between surveys, do your maintenance, right? If we can get to that, that would be super efficient. And autonomous is safer, faster, with lower emissions. And we move the crew onshore and supplement that with offshore robotics. So with that, I'd like to thank many different parts of BP who are continuing to support this work and drive it forward, and our collaborators as well. So thank you for your attention.
Okay. Thanks a lot, Ted, for this very informative presentation. I'm sure that this will trigger many questions during the Q&A. It's also, I believe, a nice introduction for the next two talks. Let's move on to the second speaker of the session, Fabio Mancini. Fabio is a chief geophysicist at Blue Ocean Seismic Services and holds a PhD from Edinburgh University. He has more than 20 years of industry experience working for seismic contractors and major oil and gas operators. Thanks to it, he developed strong expertise in seismic processing and acquisition and got first-hand experience of new technology deployment. And today, he will talk about the development of a novel acquisition system based on fully autonomous ocean bottom nodes. Fabio, you have the floor for the next 15 minutes or so, if you're ready.
Yep, yeah, I am, Guillaume. Let me share just the slides. And I'll make it. Hold on. Right. Can you see the screen?
Yeah, perfectly.
Fantastic. Can you see the mouse as well?
Yeah.
Excellent.
Yes,
excellent. Well, thank you very much for the introduction, Guillaume, and thanks, Ted, for the introduction talk as well, because it's really flowing into this talk. And you've seen what Ted just mentioned. So the motivations of why we want to do an autonomous system to replace static nodes. There are a lot of reasons, but if you go really to the bottom, is that it's clear that in the industry, we now know that OBN delivers superior data quality compared to streamer data. But the big issue is the deployment. It's time consuming, and so it's expensive. And for this reason, nodes have been really confined to really high value projects, or when nothing else works, like in subsalt Gulf of Mexico, Brazil. But what we want to do is try to break this paradigm of superior data quality for a very expensive acquisition, and we think we can do that with a system based on long endurance, full autonomous, and self-repositioning nodes. And this is what we are trying to develop in Blue Ocean. So on the agenda, I'm going to start just with a quick overview of the entire system. And the central part is obviously the units themselves. And you can see the current unit is here on the right. And this is it's really a classical glider, but it's got hybrid propulsion. Is use buoyancy, but also use thrusters. The difference with conventional gliders is that we have two bladders, one on the top and one on the bottom, and this is for increasing efficiency. Also, obviously, we can land, which is not something that a conventional glider do. The unit itself is also being given a high level of intelligence and autonomy inside the unit, and this it makes the unit really autonomous. What I mean by that is that when the unit just need to be provided with information from a network of acoustic communication in the surface, and the unit itself can calculate its relative position when it's underwater. And if it's pushed, because of the current, if it's pushed from this ideal trajectory toward the target, the unit itself can recalculate what is the new optimal trajectory and reposition themselves to the new trajectory. This is without any intervention from the user. So this is the intelligence and the autonomy that has been built in these units. And obviously the units are capable of landing. This is where we are going to record data. The payload is inside the unit. It's also able to reposition themselves to the next target without coming to the surface. So the idea is to roll the patch continuously without having to wait, so that the survey can be highly efficient. One kind of consequence that it wasn't really developed on purpose, but one of the consequences of the fact that we are a buoyancy-driven mechanism is also we have an adaptive weight into the coupling. Basically, the maximum weight that we can apply to our units is 4.5 kilos, but we don't have to apply all that weight once we land. We land with only a few grams of negative buoyancy. Then we can decide what is the optimal weight. So in some really soft sediment, we may decide that actually we want only to apply a force of 2 kilos and not the entire 4.5 kilos. In terms of the geophysical payload, for the moment we're using an industry standard payload. It's a 4-component, and the clock is an oven compensated crystal oscillator. So the payload is really an off-the-shelf package that we bolted into our units. For people that are not familiar with the buoyancy, I'll show you here just a video on a test tank where we, at the moment, the oil, we're pushing the oil from the outside into the inside the reservoir here. So the unit become heavier because these two parts get filled with heavier water than the oil. Now we do the reverse. The oil is pushed from the internal reservoir into the two bladders. We expel water, and the unit become positive buoyancy, and they start to emerge again. You can see it's a very gentle movement, which is really important when we are working close to infrastructure. The unit, when it moves, it only weighs a few grams. So even if it comes into contact with something, it's not something that we are really worried about. And the way we think the deployment is going to work, basically the unit, we call it the observer, can land on the seabed either by a single dive, or we can do multiple inflection. What we call the inflection is when we change the buoyancy from negative to positive. So we move into the kind of sawtooth trajectory, and we can land at determinate predetermined positions. What we need to guide is acoustic information from the surface. This will tell the unit where they are, and then the unit autonomously, as I said, will reposition. Then the units, once the unit are triggered to change to the new position. The unit can just take off and go to the next position until their mission is it's over. So this is the kind of system that we have in mind and we are using to guide the units and the kind of movement of the gliders. I'll show you now an example from some active tests. Obviously, it's all well that the unit moves, but it has to couple to the ground. It has to record good seismic data. Otherwise, they're not much use in the seismic world. So we did a test both in 2021 and 2022 in Blyth, offshore the UK, where we put our units next to conventional nodes, and we shared the identical geophysical payload with those nodes and the identical electronics. So it's really an apple-to-apple comparison. And then we shot some 2D line. In the interest of time, I don't have time to show many more results. I just published, there is a paper on first break with some more data, but this is probably the key image and shows the importance of the shape of our unit. What I'm showing here is on the top, you have the vehicle that we have designed in 2021. And this vehicle was really optimizing the gliding capability, the navigation. But obviously, we underestimated this capability or overestimated this capability to be stable on the bottom. These seismic images here, this is is a single receiver gather of the Y component. I chose the Y component because it's actually the one that is more sensitive to any rolling, because it's the component that is actually horizontal on our unit. And you can see here in 2021, here on the left, this is the result for one of our nodes. And this is the result for the control nodes. And you can see because of the instability, we're basically recording just noise. And this noise is really enhanced on the low frequency. That's why I bypass these panels to a maximum of 6 Hz. But then after a lot of work on redesigning the unit, including computer fluid dynamics, lab test, we come out with a bit more sophisticated shape with a different underfloor as well. And then we tested again. And now you can see here on the left is our node that did not, here on the right is the conventional node. You can see that in terms of signal to noise, in terms of data quality, we are really equivalent to the conventional nodes. The other testing that we carry out frequently is what we call the functional tests. Those are tests that we do without an active source. So it's really easy in that sense to go and deploy this unit, either in the UK, a lot of time in Australia, where the weather is slightly nicer. And we can do that without any permit request. So what we try to do in this functional test is really to verify the behavior of the unit in water, their autonomy, our capability to guide and navigate the unit and the entire really system that we have in place to complete the operation. What we try to do is really carry out multiple full acquisition cycle. And by acquisition cycle, I mean we navigate to a target, we land at the target as precisely as we can. We do some passive acquisition, and then we reposition to the new target. Really try to mimic what the real acquisition sequence would be. And what I show you here is one of the results from a recent test that we did last year in Loch Lynn in Scotland. And this was a major milestone for us because it was the first time that we were able to operate multiple vehicles at the same time. On this multiple vehicle, we performed multiple full acquisition cycles. So we navigated, we landed, we did some passive acquisition, we repositioned again. And what I show here on the right is a screenshot of the USBL tracker, and to show what we do with those units. So the unit here was landed at this target here in yellow. Then you can see the dotted red line. This is the unit now moving toward the next location. And what you can see here in this arrow, the unit now is overshooting because of the currents, is overshooting the target, but autonomously recognize that and loops around and moves toward the target. And you can see here in this diagram that toward the end of the test, we got better and better. We were able to land within a 10-meter accuracy, in some cases even within a 5-meter accuracy. And although we were on a lock, actually the conditions were quite challenging. We had high tide, we had some freshwater layer because of snow melting off the mountains, and there was some quite high current at the surface. And furthermore, there were a couple of days where the weather turned to be quite nasty, so that we couldn't perform any ROV operation, but we were able to continue our program underwater without having any issue at all. So that's one of the advantages of the fact that the unit don't need to emerge to reposition themselves to the next location. You can operate in conditions that usually can be prohibitive for ROVs. And finally, I just want to do an exercise in a modeling exercise to show what a full system would mean in terms of a seismic acquisition. And I use as an example the seismic acquisition, an OBN acquisition was done in Australia in 2015. It's called the Gorgon field. It's an acquisition that was done for Chevron. In this case, I have updated the parameter to make it more modern, in particular FWI friendly. You can see from the movie here, the rolling direction of the node. In the dense patch is actually the patch that was acquired in 2015. And here, to make it more modern, I put a halo of nodes in a bit more sparse configuration. So you can see here the parameter, the node spacing was 375 meter. And I kept that for the dense patch, but now I put a halo of 700 by 700 meter. Initially, this created a continuous maximum offset of 5 kilometers using 954 nodes. I extended that to have a 12-kilometer halo, and you need 1,581 nodes to cover a total of 4,000 receiver position. On the source side, I assume a triple source instead of a dual source to speed up the survey, and I kept the same source carpet. When we simulate that with a time motion simulation, you can see here the results. So for an ROV-driven OBN, it will take about 95 days, and this is without any mob of the mob included. And when we use our units, you can see that the time is almost half. It takes 55 days. This image here shows the vessel activity. In red is the waiting time. So you can see that for the OBN, the source vessel has to wait most of the time. So it's really limited by the receiver movement or lack of movement of the receiver. In our case, the situation is actually reversed. The unit can move faster than the source has to shoot between them. So this has opened up the opportunity. I think Ted mentioned it as well. If you're happy with blended solution, then open up the opportunity to actually using 2 triple sources. And now the survey become balanced, and it would take 32 days without any downtime and mob de mob. So this is the opportunity that repositioning nodes can offer compared to static nodes. Other opportunity, this is more for an exploration style, but I use Gorgon anyway, just to highlight, is to have a hybrid survey when you have a streamer survey, but you also have a set of sparse nodes that you use for velocity information for FWI. In this case, I use a set of a classical 12 streamer 75 meter separation with a triple source. So this would be quite a dense survey from a streamer. And then I put a grid of 900 meter by 900 grid nodes. And that's a total about 1,000 nodes. Those nodes will be deployed at the beginning, then the streamer goes and then will be recovered at the end. In this case, the simulation showed that the entire survey, included the nodes, will take just 16 days. So what the interesting aspect of the hybrid is that it's only attractive if you have an efficient nodal deployment system. It's a concept that I think from a geophysical point of view is well understood, but its limitation is really the high cost of deploying the nodes. And this is because even in shallow water, the node on a rope are really not suitable for this kind of sparse deployment. And the ROV, as we know, they are quite expensive. And the hybrid also offers several advantages, even compared to just node or streamer alone, because the imaging is done with a data set with a really good near offset coverage, is the streamer. And then the velocity, you have this ultra long offset. In this case, we would have a long offset up to 40, 50 kilometers with this acquisition. You can also then think about having the streamer much shorter. In fact, the maximum length of the streamer is only, because the streamer only used for imaging, can be really just the inclusion of the reflection angle. So very often in classical geology, I'm not talking subsalt, a 4 or 5 kilometer offset with the streamer would be enough to do the imaging. Also, you could use, if you start co-imaging the data set, you can think about using the data from the nodes to replace infilling gap on the streamers. And also, the node can be used to run the shoot obstructed area. So you could also have a denser patch on nodes around platform, and you avoid to do multiple passes of your streamer vessel. And this solution, I think, would be quite interesting for large-scale exploration. When you have to cover 2,000, 3,000, 4,000 kilometers square, I think this augmented data set could become the norm. It's a well-known fact that in more simple geology, if the velocity is correct, then a narrow azimuth data set can provide an adequate imaging. So I conclude here. I presented a novel concept for a seismic acquisition. It's a system that, as a proof of concept, has been validated via 2 active tests, but multiple functional tests that we ran in Western Australia and the UK throughout 22 and 20 years. And we have additional tests scheduled to demonstrate the capability to scale up the system over the next year. In the survey design, I hope that I showed that the potential benefits that having this system could provide in terms of efficiency, in terms also of creativity in different design. Having the nodes that are not limited by an ROV or by a rope really open up the opportunity to be creative in terms of survey design. And with that, obviously, I want to thank BP and BP Venture that have been the main support for this project. The Clare joint venture for extra funding to carry out the test, and Woodside Energy Blue Ocean Monitor as well for the support. And yeah, that's the end for my presentation.
Thanks a lot, Fabio. Thanks for showing us this very promising acquisition system, and we are looking forward to see large-scale experiments now. Yeah. Okay, in terms of timeline, we are completely out, but that's fine. Let's continue with Christian. Let's continue to explore the roads towards optimal acquisition with Christian. We'll talk about the next generation of autonomous vehicle, and they should reduce acquisition turnaround significantly. Christian also a Master of Science from Birmingham University. He gains significant experience in marine towed streamer, OBN seismic acquisition, survey design, and data processing through various management positions within Polar Curse. And he is now a commercial manager for Base Geo. Christian, are you ready to start?
Yes, I am. Can everybody hear me okay?
Yes.
Excellent. I'll just start the presentation. Okay, sharing my screen now. Okay, thank you for the intro, and that's 2 very good talks, and it's going to be hard to follow those. However, I'm gonna give it a go. On the theme of the future of node acquisition, I'm going to go for a quick look into where OBN came from, bit of a brief history of ocean bottom nodes, the current industry status, manta ray and what PXGEO envision as the future, and then just touch briefly on what we're calling manta ray design, which is our tailored approach to OBN survey design. So winding the clock back to circa 1971, on the left there's some various node designs that you can see. These things were huge. A bright spark at some point in the 60s, I believe, came up with the idea of putting land nodes on the bottom of the ocean. And then various engineers were involved in coming up with marvelous ways to get these things to survive on the seabed. They were enormous, cumbersome, very heavy. They required relatively expensive hardware. Deployment was fairly tricky. You know, you're dealing with a fairly large crane on a moving platform. Component availability was an issue. Clock drift corrections were a bit of a pain. These things ran on lead acid batteries. And yeah, it was a bit of a nightmare. Then things improved in the 2000s on the right there. We've got a improved design. They were slightly smaller. They were deployed from, again, from the vessel on a crane, but they were slowly moving into node on a rope systems. In 2016, I believe it's Vidar Hovland's paper, where he talks about speed, reliability, and safety. They were getting quicker. Node on a rope was rearing its head, and basically, you know, it was quick, fairly efficient, but still relatively shallow, 500 to 700 meters or so. ROV deployment followed swiftly after. Of course, we're now down to slightly deeper depths, and then coming into the more recent years, we're now down to in excess of 3,000 meters with ROV deployments and the new technology of nodes. So moving on, where are we now? So we've got increased robustness and compact designs. I mean, these things are getting tiny now. I've seen the new designs of nodes, and they're, you know, about the size of a lunchbox. We are approaching the minimum size, however, which I'll touch on shortly. But yeah, we're getting to decent dive times now. Battery technology's moved on. They're all lithium based as opposed to lead acid. So we're getting dive times in excess of 200 days. I believe Ted touched on that as well as Fabio. And we're operating temperatures are now between about -5 to 45 degrees C. So we're operating in fairly hostile environments. Clock drifts, they're more accurately known and accounted for. And as I mentioned about size and weight, we're now, the real limiting factor is the weight. From experience and testing, we've found this so-called sweet spot. It's approximately 10 kilos, which is optimal. Anything lighter tends to move around on the seabed in currents, et cetera, and you get suboptimal coupling. I suppose I need to touch on to drop pop nodes. These are still in development, although I believe Surcell has a pretty decent drop pop node, sorry. However, these require a dunker with an acoustic release mechanism on the chase vessel. They are invariably lost at sea, however, sometimes found. And I guess they're a viable solution, but only for a kind of fairly small market because of their cost. Then we move on to flying nodes. Again, they're relatively expensive. The maintenance and repair requirements are, we envisage, quite high. You know, you're going to have a few technicians on board to repair these things, et cetera. Coupling issues as well, because of the hydrodynamic nature of the flying node. They're probably not going to be as good as a static node. A couple of examples on the slide there. We've got the TGS node, the OBX, and then the Surcell node, and on the top left is the PXGEO Manta Light, sorry. So where are we right now in terms of technology? We're looking at deploying our first commercial survey is coming up this year. We're currently testing in the pool. Unfortunately, I've not got any videos to show you of that. However, I'm going to talk about the manta ray unit. It's about the size of a station wagon. If you're not in the US, that's an estate car. It's autonomous. It's a hovering autonomous underwater vehicle. It hovers at approximately 20 centimeters from the seabed, so you have minimal contact. It's completely electrical, so there's no hydraulics, and that reduces maintenance considerably. I've got a quick video here. It should play if I just click next. So we lower the cages down and they operate in a yo-yo system. Basically, one manta ray will come down, replace the one on the seabed while the other one's being recharged at the surface. Recharge times are pretty quick. These things are really maneuverable. It's based on very well-established technology with Saab. It's called a saber tooth. Saab have used these for site investigations, military applications. It's a very, very well-established vehicle. It's a single hull saber tooth AUV. I've got a couple more videos here to show you. So essentially, we're using obstacle avoidance. So it uses, I don't want to call it AI because there's not anything AI. It's all machine learning and statistics. So basically, we can. Oh, that video didn't play. Sorry about that. Here we go. So it can avoid obstacles with recognition. It's got a full HD camera setup at the front. It's got a very high powerful lighting system. It can deploy in currents of up to 4.5 knots. It can shift pretty quickly as well. It can stop, so accelerate and decelerate really quickly. It's neutrally buoyant, and it's got controlled node deployment and recovery. This is actual footage of an obstacle being, coming up on a node or a test object. So it's got 3D mapping as well as stereoscopic vision. This one goes on a bit longer, but essentially it actually makes a full 3D image of what it's seeing, which is verified by the camera image there as well. That's just it being rastered and rendered. So onto the unit itself. As I mentioned, it's a Saab Sabertooth single hull. The manta ray configuration for node deployment and recovery basically uses standard equipment. So we're not trying to reinvent the wheel. It's node agnostic. So it will take up to 40 nodes and can operate down at 3,000 meter water depth. It can perform self-rescue. So these things are going to operate in a team of 3. 2 units are going to be operating in a yo-yo fashion, with the third on deck. The third unit has a manipulator arm, which will be used for PIES deployment. As I mentioned, it's fully electric. We're looking at positioning specs within the same realm as ROV in terms of node location. And as I mentioned, it's currently being wet trialed in the pool, with the first commercial survey coming up. So as I mentioned, it's node agnostic. It's going to be faster and more reliable than the flying nodes we envisage. It's minimum seabed impact because we don't actually make any contact with the seabed. And then what we're trying to incorporate with this is the Manta design ethic, which is essentially using customized geology solutions. And we're going to be operating, there's quite a collaborative effort with the client on developing the best system and the best node configuration in terms of sampling using the manta ray vehicle. So we're envisaging up to 50% faster node handling. In real terms, I'll show you just a quick graphic which shows the deployment compared with, oops, where's my video? There we go. So in essence, we've got an ROV deployment on the left, a manta ray deployment in the middle, and then on the right, our kind of optimized manta design with manta ray. So thereby we're actually increasing the receiver grid and reducing the source grid. And I'll just let that run because it's still going for the conventional ROV node deployment and recovery. So in terms of benefits, we're going to be reducing node deployment and retrieval times pretty much by half compared to the ROV. As Ted mentioned, you're only as good as your slowest element. And in this case, it's receiver deployment and retrieval. Many surveys are receiver bound, and you'll have the source vessel standing around for a while, costing money when you could actually be using it. When used in conjunction with manta design, we're going to be optimizing source and receiver patterns for further time gains. And we're hoping that this will, in essence, utilize existing technology in a more effective and more commercially viable way for our clients. And with that, it's nice and short. I think we're all ready for some questions and answers.
Thank you very much, Christian. Can you hear me?
Yep.
Okay, so we have one question for you. So it's from Mark Zajac. So how much of the time savings is the result of the source and receiver decimation?
Good question. So in that source and receiver decimation, there's basically, well, I think it was, let me just check my numbers here. So yeah, basically we're the third option there, the densest option. It appears to be the same, but on the more sparse receivers option. It's basically because we're adding more manta rays to that vessel to handle the increased receiver density. So in essence, I think we're looking at a time saving because of the source density coming down, but we're actually increasing receiver density. So this is where the manta ray optimization or manta design optimization comes into its own, because you can therefore reduce your source grid by increasing your receiver grid.
Okay, thank you. Mark, if you want to add any comments, you can unmute yourself if you want to. So otherwise, I don't see any other question. So we have questions for also for Ted and Fabio. Are you still there?
We are. All right.
Okay.
Yep.
Okay,
Yeah,
so
yeah.
maybe let's start with Fabio. So it's again a question from Mark. Do you anticipate the USBL cone to limit the speed that the nodes can position and reposition themselves?
Yeah, no, that's a good question. So the USB cone is one of the issues, though it's really depending on what the water depth you're operating. But what we are envisage is not just one USBL. We envisage to have a network of acoustic communication in the surface, probably driven by autonomous surface vehicles with other USBL. So we want the unit has to have at least 3 different acoustic positioning to really calculate its position in X, Y, and Z. So there will have to be a network. It's not going to be a single USBL. And in shallow water, this network had to be more extensive. In deep water, actually, the cone is pretty deep, so you will have fewer units in the surface.
Okay, thank you very much. So that's the only question we have. And we only have questions from Mark. So if anybody wants to ask another question by unmuting himself or writing in the chat. Okay, we have another question actually for Christian. For the manta ray, we still need to use the same fleet on the survey. Is any planning to recover the units by the support vessel or a reduced size node vessel?
Yes, is the answer. It's I don't quite think it's going to be a containerized solution. However, yeah, it has fairly minimal requirements in terms of vessel capability.
Okay, thank you. That was a question from Felipe.
Okay, the biggest restriction, I guess, is deck space, because these things are quite large. As I mentioned, about the size of a car, and we've got 3 of them on board, so you can't put them on a tiny little thing. But equally, we don't need a super tanker.
Okay. There's Mike Boysen who's asking, would you consider using sparse LBL?
Yes. Yes, we are considering. Yes.
Okay. Okay. There is another question. So there are now questions for Ted. Okay, let's start with the first ones, maybe. So from Mark again, are regulators on board with the introduction of autonomous technology? And will they let you fly into that wind farm, for example?
Yeah, so this is a great question. What we found is that small USVs are already commercial, so they're already being used and in and around wind farms, and they have they won't even chip paint off anything. So that's fine. That's already known. But I think what the gist of my talk was not what's commercial today. It's the going upscaling and getting bigger. So with the blue ocean technology, the idea is to bring in the larger vessel but stand off well outside any projects. We haven't done that yet because obviously we haven't built sufficient inventory to test that yet. But we are working with the regulators in the US at the moment to actually, we've talked to BOEM and BSEE and NIMFS and the Coast Guard on these plans. The slide I showed you about our field trial is here. So again, every country, every coastal state will have its own rules. But what we see is there are already passenger ferries which are autonomous, right? So probably the hardest one, where you take people off out of the crew and put people on as cargo, that one is already operating. So I think it's kind of an unusual situation. Just shows that this is really going to gather pace, but it's not approved yet. The other side is, if you have to bring in streamer vessels, we have several examples in the North Sea of carbon capture surveys, right? So we're over a carbon capture use area. We then acquire a 3D survey to actually map out that reservoir before we'll be injecting. What will be wind farms built on top of many of those that are already in planning. You will not be able to bring back in, never be able to bring back in a large streamer vessel, right? So if we have an autonomous vessel which sits off outside the area of concern, the safety zones, and then we inject in, let's call them gliding nodes, then they will just glide into that infrastructure with zero harm. Now, have we proven that yet? We've proven in principle that they glide in and land and come back. We haven't proven we'll be allowed to do it, right? But obviously, it's a lot less risk than bringing vessels in.
Okay, thank you very much. So another question again for you. Let me find it. So how does the cost of an autonomous node compare to the cost of a conventional node? Still from Mark.
Okay, it's a good question for me because I know the answer, but I can't tell you. All I can tell you, Fabio can't tell you either, just in case you ask him next. But what we can tell you is that the design is basically not to be radically different than what we call a dumb node, right? Like I indicated at the very beginning of my talk, we built the first deep water nodes in conjunction with Fairfield, and we operated those at Atlantis in the noughties, right? So 20 years ago. So we know what it takes. We've more recently built the land node, so we know what the geophysical package is and other stuff. So while we're not experts in this, we have a pretty good idea of what the cost should be. And we obviously, any of the scenarios that I talked about, a very quick scenario, we increase the cost of the survey for that new equipment, right? So we're doing apples for apples comparisons, so that basically the new kit that you have to build, and which by definition has more stuff in it than just a geophysical package, right? So it's clearly not going to be the same cost. It has to be somewhat more, but not, I would say not, it's not destructively high in cost, because if it is, we wouldn't do it. That's about as much answer I can give you. And the point is the efficiency of the operation way outweighs the additional cost then for the inventory. And that's what I was trying to make the point on. We have so much inefficiency operating the equipment, and those cumulative day rates we can afford to increase the cost in marine for the sensors. In land, we cannot. We went the other way. In land, we wanted to make them way, way, way lower cost. Then we can have many, many, many more of them. So hopefully that helps.
Okay, thank you. Another question for you from Pete Wood. So who's asking, are there any current plans for survey, principally for CCS?
Yes. So again, using the there's Southern North Sea testing that we've been working with Blue Ocean on. You know, it's all a matter of where do you put your inventory, at what pace, and so on. We've talked to our partners, BP partners, in that regard as well about these technologies. We've even discussed with other parties about other sensor packages, right, that we might do for CCS monitoring, not just from a seismic point of view, from other sensor packages. But there is we haven't done any, just to be clear, any proper full seismic survey with this technology yet. It's still a prototype, you know, about 10 prototypes, right? That's not sufficient to do imaging yet.
Okay, thank you. Before opening the mic, okay, one question again for Ted, who's so it's Mehmet Tanis, who's curious, where does Clearfield test map on your trace density graph? Sorry, I'm just reading, so.
That's very good. I did put it on there. Let me try and see if I can recall. I think it's about 25 million, yeah, versus 100 million. So the 100 million is the trace density linear best fit, right, from an exponential density increasing. And we achieved on the calculation 25. Now, that's not to say we deployed enough equipment to do that. That's just using the 20-kilometer area, and you'll have some gaps in that because you didn't deploy enough equipment. But on a sampling basis, yes, we were under.
Okay. So now a question for Fabio, and then we will let people just directly ask their questions. So is there a depth limit to operate? And also, is there any thought on the cost comparison of conventional versus autonomous units themselves?
Okay, I mean, the second question was already answered by Ted.
Yeah.
There is a difference in cost, but it's well compensated by the operational efficiency. In terms of the depth, yes. So we sorry, the lights keep going off in my office. Yes, at the moment the units, our prototype can go up to 500 meters, but the commercial product will be a deep water, will be extended to a deep water. Whether it's going to be 2,500 or 3,000 meters, we still have to really finalize what the consequences of this extension depth means in terms of size. So will be some compromise, but the objective is to go to a deep water unit that will be able to operate around the 2,400 meters.
Okay, thank you. So Watik, maybe you can unmute yourself if you want to ask your question.
Thanks. Sorry, so it's a question for Ted. We've heard tonight about receiver efficiency, cutting deployment time by up to 50%. So my question regards on the source side. Now, when we have shot-bound surveys, is BP happy that the current source efficiency is fit for purpose to catch up with that ostensible increase in receiver efficiency? For example, is SimSource fit for purpose, or do you think that there need to be more evolution on the source side as well to keep up with this deployment rate?
Yes, great question. In short, yes, I think we're happy with blending. We've been doing it source side blending for many years in the marine side for ocean bottom data as well. There is a question with some of our partners on, for 4D, what is the amount of noise residual that you have from that versus a very weak, say, 4D signal? The simple answer is, as soon as you increase the density in sampling, improve the imaging algorithm, the noise floor will go down, just because you have sampled everything so well. So therefore, we can tolerate actually some extra noise from the source side. So you can just use conventional sources more often, but there's a case-by-case basis. Very, very weak 4D, you may want to be careful with that and do some studies. The other side is, yes, lots of interesting changing on the source side. So we're going with smaller sources and autonomy, which means we will pull single sources, whereas because little small marine vibrators, for instance, on small USVs, which means you can afford to have many vessels for the same cost as one conventional big vessel, which is towing 2 big air guns, for instance. But of course, the industry's also got some really nice wide tow capability. And of course, you can look at different schemes with that. You have a bigger paintbrush. You can tolerate, therefore, a bigger day rate cost for that vessel because you cover a lot more sources. But they tend to be smaller as well. We're spreading out the equipment into smaller subarrays. And we are getting some element of blending as you start increasing self-blending, if nothing else, all the way out to random. You can do, BP call it popcorn, but E-seismic, is another approach and others. So I think if you start deploying other types of distributed sources, that's the other angle. You may not want to bring out all your bandwidth in one source in the future. You may bring out one small source with low frequencies, and that'll be relatively sparse, and then you'll bring out lots of medium to high frequencies and have those moving around independently as well. So that's probably the way I suspect we're going to end up.
Thank you.
Thank you. So let's maybe let Artem ask his question.
Okay, thank you. I have one question to Fabio and one to Ted. So Fabio, you mentioned about sweet spot weight for the nodes. So do I understand it correct that for your technology, for your nodes, the question is about coupling. So they are just landed on the seabed and they are not doing any actions to improve coupling. Is that the case?
Yeah, that's correct. So they landed with a very low weight. They will be only a few grams when they land, and then you keep pumping the oil in the internal reservoir. And overall, at the moment, the maximum mass weight that we have for the unit is 4.5 kilos. But coupling is quite a complicated field, actually. And in very soft sediments, you may actually prefer to be lighter if the current don't move the unit. So in that case, we may do tests and see that maybe with 2 kilos, the data are better than with 8 kilos. So we have this ability to basically change on the fly the weight of the unit on the sea bottom, but there is no any active movement. The unit doesn't have any moving part outside. So the unit just glides, lands, and changes its mass.
Okay, I see. And there is no, you don't really check the actual point. So you have an opportunity to land like 10 centimeters left or half a meter to the right, or do you do something like that?
So the precision will be, I mean, again, depends on current. We think we will be around the 10 meter or less of precision. But what we are building in the units is the capability to automatically reposition themselves if they land suboptimally. So if they're landing on a rock or they're landing in area that the receiver is not stable, the unit themselves have the capability to say, okay, no, we are not stable here. Let's just move a meter off, and with just the thrust that they're just moving, lifting a bit and moving. So we will have this kind of capability in the unit.
Okay, that's great. Yeah, that's really what we are missing, like in a stationary, non-smart nodes. Yeah. Okay, thanks. And one question to Ted. Maybe I missed it, but you mentioned about these fully autonomous source vessels, or maybe source and deployment retrieval vessels. Is like a near future, or do you really already have some data acquired or some projects acquired with this technology? Thank you.
No, great question, and I apologize. I rushed through a lot of stuff, so I'm just happy that you even picked that up. But in essence, we will be trialing it this year, and this will be the first year. It's the first year the vessels are operational, right? So we've had to wait until they've been built, tested. Like any new vessels, you have to go through a range of stuff. So we have a plan for 2024, probably towards the second half, to bring out a marine vibrator to the Gulf of Mexico. autonomously deploy that into the water, acquire a 3D grid of source points, sort of autonomously operating it on a grid, and then autonomously record it, retrieving it. We'll do some extra stuff as well, but in principle, that we're doing that with the regulators, so we have to permit that, which is, as I said, in the US, it's called a new and unusual technology, so it's a NUT, and it goes through a slightly different process on permitting. So we intend to go through that journey and share it. It'll probably be EAGE next year when we share the outcomes of that. It's not done yet, no, but we are planning on doing it this year.
Okay, yeah, thanks. This is like sounds like a first step for Elon Musk technology to repeat the same on Mars. Yeah, thank you.
Yeah.
Okay, any other questions, Artem?
I also had thank you, Fabio, for your reply, and thank you, Ted. I also had a question about these slim sources, but I see that Nick Moldavani asked the same in the chat, so I don't have more questions. Thank you.
Okay, thank you. So a quick question for Ted. What is Explor's pinpoint source?
So yeah, Explor, EXPLOR, so Explor. Okay. Canadian company. Alan Chatanet is on LinkedIn. You can see those devices. He shared some images of them in the Middle East. I think an array of 5 in the sand dunes. So go look Al up. Since it's his technology, I'll refrain and just say it's an impulsive source, and it's very, very low energy. So we're talking about kilojoules, not megajoules, right? So we're normally used on land using megajoules, right, and dynamite and what have you. But this is a lot lower, and it's still, as you saw, quite an impressive image. And that particular coupling in that particular geology, as ever, all the caveats. We won't guarantee it works the same everywhere, but it's impulsive and very weak.
Okay, thank you. So one last question for all of you, actually. So from Mario Sergio Costa, who's thanking you for excellent talks. So he said that it seems that not to operate autonomously all the way from the vessel to the ocean bottom is an advantage, like less battery needed, he guesses. But otherwise, to reduce the size of the vessel using unmanned technology should even be better cost-reducing strategy. Do you agree? And please comment.
I'll quickly answer. I disagree. So I think what we laid out was bringing let's call them the nodes for the sake of simplicity. Bringing your nodes to the project area with a taxi, a vessel, makes sense. But once you're there, then letting them in the water from the surface and letting them go down is what we actually propose. So we think it's an advantage. Now I'll let Chris talk to his method as well, because it's different indeed. There is indeed extra battery needed, but it all comes down to what is your overall mission and endurance. Buoyancy reduces the amount of battery that you need. That's the point of going to buoyancy. Propelling yourself up and down, of course, would use more battery. So there's a nuance in the question. You're quite right. For us, the answer would be no, but I'll let Chris talk about his next.
Thanks. Cheers, Ted. Yeah, I think from our point of view, I think I mentioned we're node agnostic, so we're using existing technology. And in terms of battery, the nodes that we're using are the industry standard, so we're getting up to 200+ days, etc. Now, I can only assume for a flying node that it would, you launch these things, they land and then go into some kind of dormancy or sleep mode, and then get reactivated when you come over with the vessel or whenever they're needed in terms of shot halo or just general recording. But I guess from our perspective, we're trying to optimize what's already out there in the industry, rather than the likes of Ted and Fabio, who are spearheading the new technology in terms of the actual node itself. Although we're PXGEO are developing our nodes as well, but yeah, it's a different approach to the same issue. But I would argue that the manta ray leverages the technology it makes do with what we've got in a more efficient way.
There's room for all of these solutions, by the way.
Yeah.
This is a growing market.
Exactly, yeah.
You know, so I'm very encouraged to see more approaches, and again, our industry prefers that as well, because we don't rely on just one, and we all learn from each other. So I think, yeah, room for all.
Yeah, let me adjust on the batteries. Is that when you look at the economy of an old survey, we did the calculation. Basically, 99% of the time you're actually in a passive state, recording data. So what we're actually trying to optimize is the geophysical sensor. That's actually the clock is what drains a lot of the batteries.
Yep.
Okay, I think this is all for the questions, except someone wants to raise his hand. I think no. Okay, so I think we're done.
For those interested by energy transition topics, we are glad to inform you that we have this technical session dedicated for carbon dioxide and hydrogen storage in geological formations. So the event will span over an entire day.
It's an in-person event, and I think the number of seats is quite limited. So feel free to register as soon as it's online. Thank you for these super interesting talks. And
no, thank you. Thank you for organizing.
Yeah,
thank you.
Thank you.
Bye-bye, everyone.
Thank you very much. It was perfect.
Thanks, everyone. Very well organized indeed.
Yeah, thank you, Paris, for organizing this and for inviting everyone. Yeah, thanks a lot.